Um, so I'm Jacob Tomlinson. I work for the Met Office. My background is in Linux system engineering, Linux system administration, and deployment. And before that, it used to be in web design. So I kind of went from a bit of an application to a kind of more managing systems environment. For those of you that don't know who the Met Office are, the Met Office is the UK's government weather forecasting organisation, and we also are home to the Hadley Centre, which is a climate research organisation. So we're quite a large organisation. We've got things like supercomputers, which churn out terabytes of data every day. We then take that data and do research on it, we do analysis on it, and we turn it into products as well. I'm specifically part of the Informatics Lab, which is kind of like an R&D kind of team within the Met Office. So we look at what's coming up next and do something which people keep referring to as technology pathfinding. So we're trying to figure out what bits of technology are going to come up. As you can imagine, we're a government organization, so things don't move as quickly as a startup. You can think of us as like the opposite of a startup, basically. We've been around for about 100 and something years. So we move slowly and cautiously. And so my team is involved in looking at what's coming next. So what I wanted to talk to you today about is in two parts, really. It's half an hour. I always think half an hour is quite a long time to talk for. So I'm going to talk to you for a little bit about our use case, which is something to do with visualizing our four-dimensional weather data. And then the second part, I'm going to talk about something that's a little bit more high level and something that I call confidence in integration. So we'll start with the visualizing 4D weather data. So we have an issue with the fact that our supercomputer spits out these really nice, rich, 4-dimensional, 5-dimensional, 6-dimensional, whatever you like, weather simulations. So you've got your longitude and latitude and your altitude, and then you've got time. And then you've got whatever the thing is you're wanting to look at. So that could be clouds, it could be temperature, it could be wind. There's loads of different variables. There's a couple of hundred, I think, that come out of the model. So we want to find a way of looking at that as richly as possible. But because of the size and the scale of this data, it gets really difficult. And for an operational forecasting point of view, from like realistic perspective, they have to abstract all of this away into graphs or maps with 2-dimensional weather layers over the top of, or even a map with suns on it to get that information across. But we're doing a physical simulation of the atmosphere. You know, you get a really rich, nice piece of data out of it. So why can't we look at that? Why can't we use that to get a better intuition about what's going on in the atmosphere? So specifically, the part where Kubernetes and containers came into our use case was all to do with about ingesting that data and getting that data from the supercomputer to the person at the other end of it. So we as an organization put time and effort into looking at broadcast quality renders of the weather. So, you know, you turn on the TV, you watch the weather forecast, you can see some really nice weather graphics. But those things run on very expensive computers with big render farms sitting in a data center somewhere. And that's great for broadcast media, but for our hundreds of scientists that are sat in front of their Linux desktops, or people sitting at home who want to look at the weather in this kind of way, they don't have access to this hardware. So we needed to come up with a few additional constraints that allow you to look at that. So the constraint that we added was we have to be able to do this in the browser. So we start out the supercomputer, and we want to get this data into a web browser. As you can imagine, the data that comes out of the supercomputer is not very web browser friendly. It's a binary format to cover however many dimensions of data you want to deal with. And web browsers like pictures and text and things like that. So one of the things that came out of our team is a nice little pipeline that takes this binary data and gets it into a nice web-friendly format. So we tried to look at different formats and how the data can be kind of squeezed into a different type. And came up with the fact that our data has a time element to it, and videos have a time element to them. And videos are really good at compressing time-wise. So we're thinking, well, if we can put our data into a video, then we get that nice temporal compression. Because this data is big, so these binary files that come out, to look at cloud for 36 hours, it's about 5 gig of data. So loading that in memory into a web browser is just not going to happen. So we're trying to look at quite compressive formats and quite nice ways of getting that across. So we start out with those binary files, 36-hour forecast, that's 36 slices of data. So if we convert each one of those into an image, you get some nice image compression on that already. And then we can string those images together into a video, and you get the temporal compression. So we don't normally look at lossy compression. We normally deal with lossless compression because we tend to be doing science or maths with this data. But in order to look at it, it doesn't matter if it's lossy. It's okay to lose information, especially if it's information that you can't see. You know, we're trying to get this data and just look at it and do nothing else. So there are organizations out there that spend a lot of time putting effort into making things compressy, but looking the same. So people like Netflix and YouTube, they want to take big files and make them very, very small, but look the same. So using different codecs and things. So we use PNG, and then we used Theora OGG video format, but we could have used anything else as well. We take it through a few different stages, and we end up with something that looks like this. So this is the weather data I said about. This is cloud fraction over 70 altitude layers for a 36-hour forecast. So in order to get this altitude layer into a video, we've had to tile it. The nice thing about an image is you get 3 color channels, red, green, and blue. And in cloud fraction, you just have one value for the data point. So we can put 3 altitude layers in the same block of pixels in 3 different color channels, and then tile them across the video. And then, so the video itself is something like 4096 by 4096, or half, because it's in portrait. So we tried to make the video as big as possible that a browser would be happy with, and then squeeze our data into it. So we put this through a series of containers and end up going from our binary format to this video format. We can then stream that video format into a web browser. Web browsers are really happy with that. They can take, chunk by chunk. Streaming works really well. And then we can take a frame of that video and in real time pass that into the graphics card and have the graphics card reconstruct that altitude layer out of the tiled data. So you end up going from a video looking like this to a browser application that looks like this. So you get your clouds back, you get shadows, you get nice volume rendering, and you can manipulate it, you can grab it and give it a turn around. All the data has been loaded into the browser, so you can look at it however you want. It's not a video, it's an interactive piece of information. So this is a prototype. This is available on our website. So I should have put the address up there. But if you go to informaticslab.co.uk, you can find this under projects, under demos, and you can have a look at the data. So I took this screen recording on Thursday, but this updates every 3 hours. So you can see the weather forecast over the UK. But the thing I wanted to talk to you about is this container process to get this data from the supercomputer into the browser. So as you can imagine, an application like this is made up of a couple of different service types. So we've got long-running daemons like Apache or Nginx or something like that that's actually serving out this HTML. We've also got a custom Java application that's serving out the videos and the images. We've also got another application we use called Threads, which is really good at handling our native binary data format, and you can do manipulation server-side with that. And then we've also got these short-running workers. So these are the things that takes a binary file, converts it into a series of images, and then takes a series of images, converts that into a video. So this is doing something asynchronously. It's just chugging away a list of things that it has to do. And they're a bit more ephemeral. You can kind of stop and start those as you like. You're not so worried about providing service like you are with something like Nginx. So we built this in a container format. So each of these different applications were put into its own container, and then we popped it inside Kubernetes to allow us to gain a few different benefits from this. And so hopefully, okay, maybe it's a good time to ask, who here is running Kubernetes in production? Cool. Who here has played with Kubernetes in development? Cool. Okay, so you're pretty much where we are. So we're at the point where we're looking at what benefits we can get from Kubernetes and how we can leverage it to improve our use of resource and speed up our development time. So one of the things that I found really, really useful is mixing these job types together. So instead of having to have web servers that serve websites and job servers that do jobs, we can have these mixed servers that are doing multi-tenancy, and then we can do a little bit of vertical scaling on top of our horizontal scaling. So I'll show you that here. Imagine we've got 3 Docker hosts, and we've got 3 Nginx containers in there that's serving out this application. These are sitting behind a load balancer, and they're just getting requests all the time. Now, it's the middle of the night. People are using it. They're sitting at about 30% CPU usage. That's fine. Then people decide they want to go on our application. So they start hitting Nginx. Its CPU usage ramps up. Its memory usage ramps up as more people are using the application. goes back to being nighttime, Nginx ramps back down again. So we've got this 70% of overhead on these boxes that's waiting for this capacity change, a change in requirement for the capacity. And that seems a bit inefficient. You've got this kind of lump of server that you're not doing too much with. So why don't we pack a load of workers in as well? We've got all of these jobs that we want to convert binary files into images and images into videos, but they're not so time sensitive. If I go on a website and it doesn't serve me the HTML back immediately, I'll be annoyed. But if our job server has to wait for a little while before it can do something, it's not such a big issue. So in a situation like this, we've got all of our workers sat with Nginx. Loads of people go on it. Nginx ramps up. It just kicks off a load of workers. It just boots them off the box because they're lower priority. So we can get really responsive scaling on the Nginx box, and then the workers have to figure out what to do in a bit. So what we started thinking about then is, well, what if the demand for our application goes up and continues to be up or stays up? Then we need to start thinking about horizontal scaling as well. So one way we can approach this is we're still not quite sure what Nginx is doing. It might be going up, it might be going down. We haven't used this application too much, so we don't know what the demand is going to be. So let's just start another box and fill it full of workers. So if Nginx does go back down again a bit later, we can just shuffle those workers back onto those boxes and get rid of that host again. Or if Nginx stays high, then we can start another Nginx worker and redistribute again. So you end up shuffling all of these containers around, and you end up going from a 30% average utilization of your box to an 80% utilization of your box, and you're making far better usage of your hardware, or especially if you're paying for something like Amazon EC2 instances, you want to get the most for your money out of those EC2 instances that you're running. One issue with all of this is persistence. It's a theme that I've seen all day today. We've got these applications that are holding this data. So we've got our binary data serving application, and then we've also got our video and image serving application, which is sitting on top of a Mongo database. And we don't want to lose those. So we don't want containers jumping around too much, otherwise we'll end up losing our data. So we used EBS-backed persistent volumes in order to keep data consistency across our stack. So we're building all of our stuff in AWS for doing our development, and we've played around with EBS Volumes. So just in case you don't know what that is, it's just a virtual hard drive, basically, that you can attach to server instances. But Kubernetes is aware of this. It knows how to deal with those as a storage backend. So you can designate a persistent volume as an EBS piece of block storage, and it will attach it to the host. So you end up in this situation where we've got our Docker hosts. One of them is running a Mongo instance, and we've got a bit of hard drive space that we want to give to that Mongo instance to keep the data in. So Kubernetes will mount that disk on that server and then mount the volume inside the container. That's really nice until you want to move Mongo. So we've decided we want to shift that one over because the host it's on is going down, or the Mongo instance has died, and Kubernetes has just arbitrarily decided to move the container. So all we have to do in this instance is as part of the Mongo startup process, we just disconnect the EBS volume, connect it to the new host, and then mount it inside. And so Kubernetes deals with all of this for you, and you don't have to worry about where your data is. You know it's safe on that disk, and that disk is going to follow your container around. Another thing we found really useful was scaling by queue. So a lot of these worker processes that I talk about, they're using transactional queues to get their work. So our supercomputer, every 3 hours, spits out loads of data at the end of a model run. So we have this huge spike in demand of converting all of this into videos, and then that slopes off again, and then 3 hours later shoots up. So we need to be able to be responsive in our hardware. Otherwise, we'll end up paying for this capacity that we're not using most of the time. So we will have, we can have a process that's sitting and looking at our queues, and it's saying, well, we've got 30 jobs to do on the queue, and we know that one container can handle that. So it will make sure that there's one container in Kubernetes. It will tweak the replica set value to ensure we've got that one container. Then the supercomputer spits out a load of data. The amount of jobs in the queue goes through the roof. And so this worker process looks at that length of the queue, tweaks the value in Kubernetes, and Kubernetes scales us up to have a load more worker processes. It can then chug through the queue, and as the queue gets shorter and shorter, the amounts of containers in behind will scale back down. And the nice thing about this is you can balance things like cost versus scale. So in order to process this work, if you fit it on your machines efficiently, you could process 10 things in an hour, or you could process 100 things in a tenth of an hour, depending on how you scale. But you're going to end up paying the same amount because you're paying per hour for your machine. If you do 100 things in a tenth of an hour, you're still paying for your whole hour to finish all of those jobs. So ideally, we're spitting out data every 3 hours. We want an hour of server time, really, to get the data to the users as fast as possible. It needs to finish as quickly as possible, but we're paying for a whole hour of AWS time. So we might as well make use of that whole hour of AWS time. And so you can tweak those values and then scale your workload based on the queue length to ensure that it finishes in 59 minutes or something like that, just to make sure you don't tick into your next hour. So we're, in this demo, only paying for 1 out of 3 hours of server time, which is nice. You could say that's a 2/3 reduction in cost compared to a standard architecture. So that's kind of how we've used it so far. And that's raised a few thoughts within the team about how thinking about projects in this way can change how we think about our legacy infrastructure as well. So as I said before, we're a large government organization that's been around for a long time. So we've got old traditional servers that are chugging away, doing a very good job very well, and we're going to have them for a long time. We're going to start looking at bringing in container infrastructure, but we can't just flip from one to the other. We're not a startup, so we can't just start with containers. We have to look after our legacy infrastructure and maintain it to keep it secure. Stateless also isn't always practical, as some of the other talks have said. You need to run your databases and you need to run your processes, but there's something I've been thinking about around state. So a database is like the perfect example of something that has state. It's got data and you don't want to lose that. But if you think about something like Nginx, that has a certain amount of state for a certain amount of time, because I want to download a gigabyte file from my Nginx server. So I open a request to it, I start downloading this gigabyte file. I live in the countryside, so I've got a 4 meg broadband connection. It would take me about 40 minutes to download that 1 gig file. It's awful. But I don't want that Nginx server to go anywhere for 40 minutes. I want that to stay there. And then when my request is finished, it can go. I'm not worried. So there is a certain amount of implied state in finishing anything that it's doing. Also, one thing I've found, being an R&D team, sometimes we start a container and then it runs for quite a while because we're working on something else. And we're kind of trying stuff out. And even though the container has been designed to be stateless, you look at it and you think, that container's been up for 3 days. Can I just restart it? I can't. I'm trying to conceptualize what this container's doing, and is it really stateless? Am I going to break anything by restarting this? Is it going to restart successfully because I've changed this, that, and the other? So again, as I said before, I've kind of broken my thought process down into 2 types of containers now. So I've got my long containers and my short containers. So my long containers are the things that run consistently for a long time, like Nginx. And then my short containers are things that may run consistently for a long time, but they're doing lots of little jobs, repetitive jobs, over and over and over on their own kind of time scale. So the way that this affects short containers is, normally you might run an infinite number of jobs. I'm going to start my process, it's got a queue, and it's just going to chug through this queue, getting a job, processing it, finishing it, getting a job, processing it, finishing it, just round and round and round, and it will just go forever. But what if I start that process and then I don't restart that process for 30 days? Say that's my security patching cycle. I want to patch every 30 days. So I could, in theory, leave this process running for 30 days. And then I might get to that point and think, well, there's been 6 deployments since then, and I've got integration tests, but how can I be 100% confident that this is going to restart okay? And one way I like to think about it, I don't know if anybody in here has ever programmed an Arduino, but if you think about the code in an Arduino, you have 2 functions. You've got your setup function and your loop function. So when you plug the power into your Arduino, it runs the setup function once and then loops forever and ever and ever. And this is how a lot of processes like Nginx work. It's got a bit of setup code and then a bit of loop code. So if you think about it, I'm patching my boxes once a month. So I'm running this bit of setup code once a month. I'm then running this bit of loop code millions of times a month. So how confident am I in that bit of setup code compared to my bit of loop code? Well, comparing those 2 numbers, you could argue that you're not very confident in that setup code because you're not testing it very often, you're not trying it very often. So we could change our short processes to only do 1 job. So the container starts, gets a job from the queue, processes it, and exits. That's quite nice, because then Kubernetes will go, oh, we're 1 down in this replica set, so I'll start another container, and that container will get a job and process it and exit, and then Kubernetes will restart it. So you remove the lifecycle management from the container itself completely. The container is there to do exactly one thing. It will do it very quickly. And Kubernetes is in control of the lifecycle of your application. There is a slight issue with that. It adds overhead. There is a startup time associated with starting a container, and although it's a hell of a lot faster than starting a VM, it still is a certain amount of overhead. And depending on what your container is doing, that may be acceptable or not. So one example would be our container that turns a time slice of binary data into an image takes about 20 seconds to run. So if our container takes 2 seconds to start and 20 seconds to run, there's a fair bit of overhead. But if you compare it to one of our other containers, which does job scheduling, that just looks at a queue and tweaks a value in Kubernetes. That takes milliseconds to run. But it still takes 2 seconds to start. So then the overhead is infinitely longer, almost, than the actual container lifetime itself. So I then started thinking about njobs. Njobs is an arbitrary number that I give my container, and I say, as maybe an environment variable or something like that. So it's like you start and run 100 jobs and then exit. So I then find this balance. So I get my conceptual simplicity, and I get my confidence in the startup code within my container. I know that it will integrate well with all my other services because it's constantly doing this. And then I can also offset that against the overhead. So depending on what the process is, I can pick that n number to be whatever I like it to be. So it's a useful thing I've found from dealing with short containers, because coming from a system administration point of view, when you get asked to do the security updates on a certain server, you might not have done the security updates on that server for 10 months. You know they've been done every month since then, but it's been by different people. I haven't touched this box, and now I've got to do yum update -y and reboot. And then I'm pretty sure that everything will be okay. This has been designed to be a flexible system. It will almost certainly reboot correctly, but I don't trust it because I haven't dealt with it in a long time. So I sit and watch it boot, and then it gets to the end, and you see it come back into the load balancer, and then I'm like, oh, yeah, that was fine. But if I'm doing that a lot, that's wasting my time. But if I look at the system and say, well, I know it was security patch last month and the month before, but I know that Nginx restarts every 4 hours. So I know if I reboot this box, Nginx only restarted 4 hours ago, not 30 days ago, and I'm more confident, and so I'm less worried about restarting this box. A good example is the other day, we were giving a demonstration to a visitor, and as he walked into the room, I fat-fingered my keyboard and totally took out a Docker host. And Docker just broke. It wouldn't run any containers. And so I wiped off all the containers and thought, right, I'll start again. Tried to start my containers, and I'd really screwed Docker, really screwed it. So I just terminated the instance and then just started another one. And we've got a little bootstrap script which just installs Docker and a couple of other bits and pieces. So I ran that, had a box a couple of minutes later. The visitor had come in then and started talking to my manager. And then I just ran our config script, which just pulls in our Docker config and starts the box up. And it started rebuilding this whole architecture then of this application. But I'd only rebuilt it the day before because I kept fiddling with it, and I keep breaking it, and I keep messing with it, and it keeps falling over because I keep prodding at it because it's research and development. So it's not such a big issue. But I could just turn away from my laptop and talk to the visitor and deal with them. And then at the point where my manager said, right, let's give a demo of the application, turn around and looked, everything's gone green, I know it's come back up, let's go over the screen and do it. And so I wasn't sat there going, oh, is it going to work, is it going to work? I just dealt with it, it booted. And so this is what I mean by the confidence in integration. I'm confident in the startup and deployment of my applications because I do it frequently. So this leads me on to think about long containers, so things like Nginx. Like I said to you, if I restart these processes frequently, it will make me feel more confident in starting them up again and restarting them. So the default behavior is to run forever, but why don't we give them a finite runtime? How long does Nginx really have to be alive for before it can be restarted? There's a practical amount of time. There's no point restarting it every minute, otherwise you'll end up with all this overhead of actually starting your service. But you can also balance that against a certain amount of time that I want to reboot it frequently to keep myself confident. So you could use your continuous integration or continuous deployment infrastructure to, instead of restarting on a code change, you restart every 24 hours and on a code change. And then you just know that your infrastructure is constantly cycling through, it's running unit tests, it's running integration tests, and you're confident that the whole thing restarts quickly. it also allows you to think about scaling down. So this is something that caused me a bit of a headache with Kubernetes. Is I've got 6 Nginx processes. The load has dropped off, and so I only need 4 Nginx processes now. So Kubernetes, I'll change that value in Kubernetes to 4, and it will go die, and kill 2 containers. It will send those processes a sig term, and hopefully Nginx can manage that. But say one of my users is downloading a 1 gig file on an awful rural broadband connection, and they're going to keep this connection open for 40 minutes. It's not going to hang around for that sig term for 40 minutes. Eventually something will come in and kill -9 that process. So that's not super ideal in terms of scaling down, because I'm going to cut that user off mid-flow. And I mentioned this to the Nginx guys earlier, and they are thinking about this. So make sure you go to the talk. I think it's next, actually, about Nginx. So that would be quite interesting to see. But I was thinking about scaling down, and why not say to my Nginx process, if you haven't had a request for 3 minutes, you should just die. You should just exit yourself. So these processes are sat there receiving requests, and they know that they should die if they get to a certain amount of time without any requests. And then in order to scale down, instead of telling Kubernetes, go and kill some processes, you say to Kubernetes, remove this pod from the service. So it then stops getting any new requests. You've got your open requests that are already there. They're holding it open, connection open to the user, but they're not getting anything new. So this might sit around for 40 minutes, allow this person to finish downloading their 1 gig file. And then Nginx will sit there saying, oh, nobody's talking to me anymore, I'm going to exit. And so my Nginx container will exit, and that scales back down, but without chopping anybody off. And as I said, it just allows you to be confident in your infrastructure. I think it's great to talk about automated deployments and scaling and all these kind of things, but at some point there's going to be somebody that's sitting behind a computer looking after this stuff, and there's a certain amount of confidence that goes into that. And so if you can sit there thinking, I haven't got any containers, I've got thousands of containers, but I haven't got any containers that are older than 48 hours. So I'm confident in all these containers deployment processes, I'm confident in my whole infrastructure, and if I get hit by a meteor and we have to restart the whole cluster in a different data center, that's fine, because the same thing effectively happened 48 hours ago on a cron job. So that's it. I would say to conclude this, a lot of the things I've talked about are about finding trade-offs between overhead and confidence. For the stuff we were doing in our prototypes, we chose some really short life cycles for some things, but you might not, it might be impractical in a production environment. So you want to kind of balance things like your end jobs against your overhead. So yes, that's the end. If you want to see this video, you can find it on our website. And if you want to ask me anything, you can find me on Twitter.
But if you want to ask him anything now,
if you want to ask me anything now, you can ask me
now's your
now.
chance.
Go for it.
So you mentioned you have some sort of scaling based on the queue size. Is that something you handle dynamically, or is there a script you run? Like, how do you hook that into Kubernetes?
So the way I played with it, so remember all this is R&D, but the way I played with it is a script on a cron job, basically, that goes, how long's the queue, tweak a scaling value in a replica set, change its name. Yeah. So it's just a script, but you could make that more intelligent, more dynamic. It could be a proper pod running in the Kubernetes namespace that's dealing with this.
Yep. Let's go back here. Yep.
Thanks. One of the problems we have in my company is with really hungry application hungry with networking. And Amazon, actually, if you want a lot of networking, you have to have a big box just because of that. Do you actually had any problem? How do you solve it with the application really hungry, maybe with networking, but not with CPU and memory?
So in terms of the scaling, you probably want to take more into account than the CPU. So if you've got network bottlenecks, like as you do, that's probably, you want to take that into account for the scaling factor. So you might have your process that's only using 30% of the CPU, but if it's using 90% of your network, then you can't fit anything else on there. So it's just about managing your scaling groups, really. As I said, we do R&D, so I haven't played with that kind of thing in a production environment.
I think there's a question over here.
Yeah.
Maybe you mentioned MongoDB is killed or dies or so. Don't you have problems with that it leaves the data on the data storage in unusable state? Like some inconsistent or whatever, that the new pod is not able to load it anymore?
Potentially. I think things like journaling helps you from that. So if you just pull the disk off and attach it to another one, your new Mongo process might discard the journal, so you lose some transactions, which isn't ideal. But as was said in the previous talk, I don't know if you're here for that, but in some situations that's acceptable, and for what we were doing, that was acceptable in that circumstance. You might want to think about doing a more distributed data set where you've got multiple replicas in your Mongo and shard across a load of containers, and then put some kind of logic in to ensure that you've got a minimum set of containers, and then have it dealing with the transactions in that way so you don't lose any. But for what we were doing, it was fine.
Sometimes AWS seems to be a bit of a dirty phrase when talking to people with Kubernetes and everything. You said you're handling scaling of instances on AWS as well. Is that being controlled by your scripts that are also handling your Kubernetes scaling, or is that typical old school AWS auto-scaling scripts?
It was typical old school AWS auto-scaling, so it was just watching for average load across the machines. There's nothing stopping us hooking into the API and making that more intelligent. But yeah, at the time it was just auto-scaling. Yeah, so it would scale, it would add new nodes, and when those nodes came up, they would join the Kubernetes cluster. And then if we were running like short-lived processes that were dying frequently, Kubernetes would then shift them somewhere else just because of the way the Kubernetes scheduling works. So that was one of the things I liked about having these really short containers that restarted frequently, is as soon as you scale out in terms of infrastructure, Kubernetes starts redistributing everything in a really clean way.
Any other questions? Oh, re-questions.
Sorry, maybe just a bit for that visualization, you have your own plugin or use some standard browser feature? Or
So it's all written in WebGL using 3JS as the library for doing that. So it's Rachel wrote this. So it's GLSL code that runs on the graphics card, basically. So it's a custom shader that does volume rendering. I had a really nice bug with ELBs, actually, in that if I removed a service, Kubernetes would decommission the ELB. If I created a new service, it would request an ELB, and AWS would go, oh, you can have that old one because we haven't got around to decommissioning it yet. So it would hand over this partially decommissioned broken ELB, and then everything would fall apart. So yeah, but I know that I raised an issue and that got fixed a little while back. So these things are a work in progress, I think, from the community point of view, but it's getting better.
Any other questions? No? Well, thank you very much, Jacob.
Great, thank you.